Sardar Vallabhbhai Patel Education Society managed RNGPIT Institute of Technology, previously known as FETR, is one of Gujarat's leading institute based in Bernoulli. The institute is recognized by AICTE and affiliated to Gujarat Technological University. The institute was established in the year 2010. The institute has 5 engineering streams: chemical engineering, civil engineering, computer science and engineering, electrical engineering, and mechanical engineering. The institute has 7 departments, including science and humanities and workshop. The institute has dynamic curriculum, robust and talented pool of faculty members, and state-of-the-art infrastructure in all the departments. It is well known for imparting quality education, active research, and also nurturing students for holistic development achieved through student engagement tools like continuous evaluation, practical-oriented learning, departmental electives, soft skills development, and many more. Recently, RNGPIT has started AICTE approved and Gujarat Technological University affiliated 3 years industry-oriented graduation program, Bachelor of Vocation on Skill Development Based Higher Education. The institute has 3 BVOC courses: BVOC in Software Development, BVOC in Production Technology, and BVOC in Refrigeration and Air Conditioning. The institute has organized 144 expert talks, 165 industrial visits, 90 workshops, 76 seminars, 32 STTPs, and 20 faculty development programs till today. The institute is proud of its academic results. RNGPIT is continuously securing top rank at state level and zone level in Gujarat Technological University. India's first common engineering facility center, governed by Setu Foundation, is being developed at our college campus. The institute has signed MOU with UGEC PowerMax Private Limited Vadodara for skill development, industrial training in wind energy, with Aspiring Minds Gurgaon for the job placement, for Trivedi Global Education Mumbai for the guidance of higher education in abroad, with E-Yantra IIT Mumbai for the development of robotic laboratory, and with Reliance Jio for the development of recruitment and training center in the field of ICT. Training and placement cell of the institute is active and alive. RNGPIT has organized 2 job fairs in the association with Directorate of Employment and Training, Government of Gujarat, and NG Patel Polytechnic. The institute has organized 2 IT job fair in the association with Surat IT Company Owners Association, SICO Surat. The institute has started SSIP cell for development of innovative projects and patent generation. Various projects done by our students have been presented at National International Expo and Enclaves. RNGPIT has established NPTEL local chapter for various online courses provided by IITs. Institute has run various skill development courses free of cost under Pradhan Mantri Kaushal Vikas Yojana approved by National Skill Development Corporation. RNGPIT has developed Hansaben B. Poonawalla Vocational Training and Research Center with 14 advanced, well-equipped laboratories. The institute has developed Tinkering Lab with the Association of Student Startup and Innovation Policy Cell, Gujarat State, in which students can enhance their knowledge in the field of IoT, robotics, artificial intelligence, 3D printing, calligraphy, and many more. The Chemical Engineering Department of RNGPIT is recognized as Schedule 1 Environmental Auditor by Gujarat Pollution Control Board Gandhinagar since 2012. The institute has around 40 industries allotted by GPCB for their audit work. NABL accredited Environmental Audit Consultancy Laboratory and Civil Material Testing Laboratory of the institute have acquired ISO 9001-2015 certification. There are many achievements done by faculties and awarded by gold medals. Every year, students have been facilitated with gold medals.
Hi, I'm Zaria Manchiani and I'm a software engineer in Silicon Valley. I did my master's in computer science from California State City Center, and I did my bachelor's in engineering in science from FETR, which now known as RNGPIT. I have been asked to share my thoughts on a few key areas. So the first one was the campus life. So I can definitely say it was both fun and STEMs. STEMs in the sense that and another thing is the fun part was that we used to have to kind of activities like something which I personally like the most activities and then there's the pressure. So in that activity, so it's in
at G Expo South Africa. In our campus, three station and presented 30 national and international journals and 30 magazines. The institute provides facility of digital library to the students. The canteen facility is situated within the college campus. All type of hygienic meals and snacks are available at subsidized rate. Our institute provides hostel facilities for our college students. Vishwasmruti, Cultural Festival Kashish, Sports Week, outbound training and festival celebrations are carried out for students' welfare and growth. RNGPIT Institute of Technology strongly believes in all-round development of the students who can better future.
Good morning, all dear participants. Myself, Professor Sachin Patel, welcomes you in this webinar organized by Electrical Engineering Department, RNGPIT Institute of Technology. I welcomes you all on behalf of RNGPIT family. Thank you for being here to be connected with us. Especially want to welcome our guest, Dr. Siddharth Joshi, sir, who is with us on such informative topic from the area of renewable energy sources and its application. Thank you, sir. Also welcome our other panel member, Professor Chinni Desai, sir, who is working as a head department at RNGPIT. Our today's moderator, Professor Ravindra Desai, sir. Now, I would like to request Ravindra sir to please introduce the profile of our today's session expert. Over to Ravindra sir.
Good morning, one and all. I, Ravindra Desai, welcomes you all. Today, once again, webinar on wind energy conversion system. For that, today we have expert Dr. Siddharth Joshi, sir, Assistant Professor in Electrical Engineering Department, PDPU, Gandhinagar. Sir, we are welcoming you all.
Thank you.
Before we start, let's give some brief information about our experts. Sir has completed PhD in electrical engineering from RK University. Sir having more than 12 years teaching experience. Also, sir published 33 research papers in national and international conference and journal on renewable energy. Sir is lifetime member in IETE, IE, and also member of IEEE. Sir guided several MTech theses and delivered lectures on renewable energy like a solar and wind energy. It's a grid integration, standalone system, and hybrid system also. So now, sir, over to you. Share your great experience with us.
So, good morning to one and all.
Morning. Good morning.
Thank you, sir, for brief introduction. I am again thankful to all of you, those who are inviting me in this wonderful session and initiative taken by the RNGPIT College. So, shall we proceed, sir?
Yes, sir. Yes, sir.
So our today's topic is on wind energy conversion system. The subtitle I have given is the basics of wind power technology and grid integration of wind power generating system. Now in previous session, I have also taken an opportunity to share my views on solar photovoltaic energy system. In that, lots of comment I have seen in the chat boxes or in the end of the video that I should more focus on the grid integration. So I have started my discussion in the impact of grid. For that, we require some prerequisite. I shall start from the prerequisite at the initial stage, and then we shall proceed further for other aspect of wind energy conversion system. So if you can start our session, so let's begin with the fun. So this is the first windmill we have seen. Right now it is in historical monument. It is a Dutch windmill concept. Now to having a heavy windmill that is of very heavy in terms of weight, we required a thorough foundation that is to be immersed on the earth body. This is one of the picture I have taken from the DTU, that is Danish Technical University, Denmark. And if you want to install a tall structure, you require a foolproof concrete tower. Sometimes it is also made up of other materials. So if you want to begin with the fun, if you not prepare this thing with thorough technical skills, it might be this thing could be happen. Right now in India, we are having a huge penetration of wind. Particularly, we are having an advantages of good sun radiation. And in that case of sun radiation, solar is also one of the important factor in the Indian power grid. But we are not receiving any radiation during early morning, late evening, and the night time. So in that case, wind is still become a massive source of energy. And if you can compare the area requirement of some megawatt of wind power generating system, in that case, wind requires a less area compared to solar for megawatt scale generation. But the problem is that in the case of rural areas, we might get a good wind, but in case of urban areas, we are not getting a handsome amount of wind. So in that context, we are having this kind of installations at open ground, onshore, or currently offshore. This is what the new technology. So in this case, our second fun is in terms of wind also. And we need to hybridize the things. So I'm going to conclude this session at the end with some glimpses of hybrid systems also. Now, if you can talk about the title of the talk, I'll start with some introductory remarks. Then I will cover basics of wind turbine, potential wind power, introduction to the turbine system. Then, as I spoke in the initial part of this session, I will try to cover grid-tied wind energy conversion system first today, then grid integration of entire wind farm. Then I will again come on our conventional way of the comparative analysis of wind generators, mode of other renewable energy system, how we can have an extraction of the power from the wind tunnel, then one of the design example of wind turbine, geometry analysis, grid integration of wind generators, that is what it has been left off in terms of simulations, simulation analysis of the standalone system, and the current work that we are doing with our MTech students, and wind farm project timeline, and the corporation of that timeline in the context of hybrid system. And then I will try to conclude and summing up my session. So if you can talk about the present grid and its management, this is what the conventional grid at present at the morning. It means that we are receiving the power in terms of mixture of all the sources. It might be a conventional power plant, it might be a non-conventional energy sources, and the grid is managed handsomely in this particular era also. But we are having a penetration of this renewable energy sources, and as you know that what is the need of renewable energy sources nowadays, you will find lots of literature in that. in the various videos and the books and the reference materials. So I'm not going to focus what is the need of renewable energy sources. This is the same present grid in the evening. At the evening time, slightly load has been increased, and according to the load management, the load sharing could be possible, but the heavy industry might be turned off at night. So at that time, the thermal power plants are working and solar is off at night and wind is working. Now you are having a various aspect of the smart grid system. So we are going to make the grid smart. So in that case, if you can go with the future grid, this is what the new system we are going to accommodate over here. This is what we call offshore wind turbine technology. If you can see my cursor over here, this is the offshore installations. We may accommodate some battery storage system. We may accommodate some hydrogen storage system. The battery storage system may be known as the BESS, that is battery energy storage system. There might be a small battery nearby our household. There might be a electric vehicles. This is one of the good options, viable option within near future. Again, if you will change the time frame, in the evening, we are having a less penetration of solar power. Our movement or the energy consumption might be fast at the residential level compared to what we are finding in the morning time. Again, at night, the solar will be off and the wind will penetrate the more power during the night. So this is the advantage of wind energy. But again, if someone can work in the wind power plant, these plants are situated far away from the urban area because they are situated in remote locations. Say, for example, desert, hill and valleys, nearby mountains, where you will find the good amount of the wind. And the most preferable locations are usually, that is what we call as a windmill installed inside the seabed. That is what we call offshore technology. If you can observe the difference, we are having the solar rooftop usually at our office premises, and that electric vehicle now is no more because they are all at their home. So you can see the considerable difference in the future grid and the grid management. In this management, the wind and solar, specifically wind, throughout the day will play a major role in the grid management section. Now, we will start discussing about the wind because our today's session is on the wind. So somebody can say that if you can define the wind is nothing but the moving air. But wind energy is the indirect form of the solar energy. Usually you will find that there is uneven heating of the land and the sea. So the sea breeze, if you can see, as a result of the sea ability to maintain the temperature, in the daytime, land heats and sea is cool. And during night, land cools faster than sea. So the change of the wind direction has been observed. You can see from this figure, over here, sea is not more hotter, sea is warmer, but land will get less time to cool down compared to sea. So this is the basic way to, or natural way to generate the wind. Similarly, this thing can be also observed if you have a concept of hill and valley. Again, during daytime, the warmer air, it will get travel on the top, and during night, the cooler air will be attracted towards the bottom. So there is continuation pressure difference. And as per the basic theorem of the Bernoulli, the pressure difference creates the velocity. And we are using this velocity concept from this wind turbine, and we are harnessing wind power from this basic principle. However, other complexities are there. So in other structure, this is the concept of the valley and mountain breezes. Usually breezes are nothing but the good amount of wind speed. There are lots of other aspects that is not covered in this session of types of wind. You will find the detailed sections in any of the book, in any mechanical engineering book, where you will find that there are lots of winds are there. Some of the wind that has been observed by Indian country are the doldrums. It's a type of the wind. Now over here, we are talking about the basics of the wind turbine technology. This technology is not new. It has been started from 7th and 9th century, where we can harness the wind power for grinding the grains and pouring the water from the ground. In the first slide that is shown over here, in the first picture, we are having the multi-bladed wind turbine, which is used particularly to pour the water. If you can talk about the very simple concept of hand pump, we can use this hand pump by using our hand. Instead of that, if you connect the shaft of that hand pump with the shaft of this rotor, easily the water will come out. Obviously, it depends upon the groundwater availability, but you will get handsome amount of water. Obviously, one more option for pouring the water from the ground is the solar pump also. But in solar system, we need to convert that solar energy into electrical one. This is totally mechanical concept. So those who are thinking that where the generator part is there, it might be not there. So they are correct. So no generator is used over here. We are just using the mechanical energy of the wind to mechanical energy. This is mechanical to mechanical conversion. Again, if you can step forward into this era, this kind of windmill you have seen, particularly it's a Danish concept, or it is known as the Dutch windmill, and it is available currently in the museums only. It's a part of historical monument. It's a kind of strip kind of thing you have seen over here. So the wind will be passed through this and it will create some hindrance and it will rotate. If the direction of wind will be changed, then someone will go to upstairs and they will reorient the rotor again. This is what the manual operation. Again, those who are not from this wind area, they need to know one basic concept. That is what everybody knows during our primary or childhood days. We are having a rotor with us and we are playing it with lots of passion. So this is nothing but the concept of wind or a windmill. This is known as fixed pitch windmill. If you have seen that rotor, we are having a round rotor and we are having a strip of ribbons stapled from top and bottom, and there is fixed pitching. One more example of fixed pitching machine, it is there at your home. It is nothing but the fan. Fan has a fixed pitch system, but the thickness of the pins are too much less, and we are enjoying the cool air at our homes and other effective use of the fan. Now, where we are standing right now, so if you can have a target of renewable energy technology by 2022, I'll not take much time on that because this data is available in the internet. You can easily browse it. So by 2022, we need to go for 175 gigawatt of renewable power plant. In my previous lecture, I tried to cover the present scenario of the renewable energy system in context of Indian grid. Now, in this case, a majority of this renewable power is coming from solar and the wind. Over here, the wind is of 60 gigawatt. Over here, for large scale solar, it is of 100 gigawatt. But in that case, this is the massive revolution in Indian grid. Is 40 gigawatt rooftop installation is proposed by 2022. So this is the massive change in Indian grid. Talking about the present scenario, we are having the central, state, and private power generating companies, and these are their shares in megawatt. Talking about the potential of wind power, from 2002 to 2019, these are the various states and the cumulative capacity of the wind power in India, and this is our current status where we are. See how steep the curve has been rising, and we are achieving up to 35 gigawatt of the production of the windmill by end of 2019. Before starting the grid integration, one must know about the general concept of wind turbine system and how it is look like. So let's look a quick video So in that case, you will be able to know that the basic aspect, and then we will have a detailed session on the grid side. So now we need to have a integration of this giant source into the grid. So for the grid-tied wind energy conversion system, the 4 conditions that must be satisfied. The initial conditions has been known to every electrical engineer is that the voltage and frequency at the grid integration point remains fixed, and it should not be vary within 5% of the tolerance limit. Now, in case of frequency limit, still it goes down. We are having a frame or a limit of 1 hertz, that is 49.5 hertz lower and 50.5 hertz upper. Within that stream or within that band, we need to integrate this wind farm. So what we need to maintain, the frequency must be close or as possible as close to the grid frequency, preferably 1/3 of its hertz higher, because we need to penetrate the power into the grid. The terminal voltage must be matched with that of the grid voltage, preferably little few percent higher, so you can pump up the electrons into the grid. The phase sequence, this is one of the major aspects of the 3-phase voltages, must be same. So if you can connect the transformer with that, so it must be of same phase sequence, and that is a preliminary rule by connecting the transformers in the parallel also. And the phase angle between 2 voltages must be within 5% of the range, so we can allow this wind turbine to be integrated with the grid. So with grid connection requirements, what we need to control? So we need to control first active power, which is related with the frequency. There is one more document available. In this document, you will be able to observe that how we can control this active power. Second is the reactive power, which is related with the voltage. If you can control this reactive power, you can easily control the voltage at the terminal end of the PCC, point of common coupling. One more document is there if you need to explore. Whenever I will share this PPT, this link will be shared by all the audience, so you can gain an extra knowledge and additional knowledge for controlling these electrical parameters. The third is most important, that is fault ride through. It is also known as LVRT, that is low voltage ride through. It is also known as fault ride through. So when there is a temporary fault or a transient fault in the grid, at that time the grid will collapse and again it will regain. So current situation says that our wind turbines must be FRT enabled or LVRT enabled. As you will observe that some of the power electronic equipments are used in the wind energy system, we are having certain issues of power quality that can be eliminated nowadays using passive filters, active filters, or incorporation of FACT devices like STATCOM or SVC. Some other issues are there, that is a generation of harmonics due to power electronic equipment in terms of voltage and current. So there are two types of wind energy system. The first is the grid-tied and the second is the standalone system. In the grid-tied system, we are having the wind generator. Over here, the new technology is that we are having a gearless technology. In that video, they have discussed about the gear technology, but gears need frequent maintenance. So we shall connect this with the direct drive system where the generator speed has been observed and it has been compared with some tip speed ratio control. This is the new word, tip speed ratio. I'll cover in the upcoming part of the session. It is the particular ratio, that is, it is the ratio of the speed at tip of the blade divided by the wind speed. As the wind speed changes, this TSR changes, and accordingly this ratio will change. As this ratio will change, we need to accommodate a tip speed ratio control and pitch control to extract maximum mechanical power from the wind turbine. Then this generator is connected with the rectifier. Then we are having a DC-link capacitor or filter. Then we are having the inverter. Then we are having the step-up transformer. Then we are having the PCC, that is point of common coupling. Then braking and triggering of the pulses could be generated by inverter control and the power control over here by generating the voltage reference and the frequency reference. We are having a facility of breaker which can be turned on and turn off this turbine that could be impacted or empowering the grid. Obviously, we need to take the voltage reference and current reference also if there is a need of the inverter control depending upon the control technique adopted. This is the block diagram of direct drive system. It is known as type D system. This gearbox in this case is optional. So if you can remove the gearbox over here, this turbine and this generator will become direct drive. Then we are having the control rectifier. Then we are having the DC-link capacitor. Then we are having the controlled inverter. And then we are having the transformer. So in the transformer, we are having the certain aspect of various components of the windmill system. Now, in case of this system, if you can remove this gearbox, so in that case, we are having a wind turbine. It is connected with the permanent magnet synchronous generator, which are comprising of higher number of poles. So if we are having the higher number of poles in this case, obviously the speed of this machine will go down. As this speed will go down, in that case, it might be a multiple pole machine. If you can talk about one of the industry, that is Enercon, it has one machine known as Enercon E53 that we are going to see in upcoming slide. So you will be able to know that what are the aspects of the system. So in that case, we have a multiple pole machine. In multiple pole machine, we are having NS equals to 120 F by P. Obviously, P is more, then speed will be less. The second aspect of the wind energy system is the standalone system. So we are having the wind turbine. It might be connected with gearbox or it might be a direct drive. Then it is connected with the wind generator. Then we are having controlled rectifier or uncontrolled rectifier. If it is uncontrolled rectifier over here, we are having the MPPT control. With this MPPT control, we can extract the maximum power. So in that case, that rectifier is uncontrolled one, and we are using the DC to DC boost converter over here. As we are using the DC to DC boost converter over here, DC to DC boost converter over here, we are having a pulse train that is to be generated, and ultimately we are getting the descending voltage. Then it is given to the controlled inverter, again 3-phase transformer and the load. Now, usually we are working in the wind farm structure where multiple numbers of wind turbines are connected. So these are the multiple wind turbines. Over here, there is one common bus where the transformer and other assemblies has to be accommodated. And these wind turbines are connected with point of common connection. Then we are having the main transformer, that is what we call the substation transformer, where entire power plant has to be merged over there or dumped over there. And then it is integrated with the grid. So this is our PCC, point of common coupling. Moreover, in the current state of art, in the electrical engineering advancement, we are having the incorporation of FACTS devices, or we can say SVC, STATCOM. So we need to connect the auxiliary active reactive power mechanism, particularly reactive power mechanism, or a FACT devices that is to be connected at point of connection. And in the point of connection, the power has been controlled. It might be active and reactive. Usually, we are having an active power pumping mechanism to generate the higher amount of revenue, but the grid has its own power factor. So we need to produce the power at particular power factor, because grid is not operate always at unity power factor. Now we are having the three categories. For the small scale wind turbine, if you need to penetrate the power into the grid, we need to maintain the frequency and the voltage constant. For the frequency regulations, the frequency has to be maintained is 50 or 60 Hertz, depending upon the country, what they adopted. So if we are having the small scale wind turbine system, we are having a range of 0.4 kV plus or minus 5%. And in that case, we are having 0.4 kilovolt voltage rating. Then we are having a transformer. Then we are having, in our case, it is 11 kV. In other grid in foreign, they are using 10 kV grid. In 10 kV grid, via common bus, we are having the medium scale onshore turbines. Then we are having large scale onshore or offshore turbines. At that time, the voltage level might be more than 50 kV or more than 1000 kV. One more option or aspect of grid integration of wind turbine with various voltage levels with, this is the new technology, that is what we call offshore one. So in the first technology, we are having a common onshore wind towers. Then in offshore wind towers, it will generate the AC power, which is variable frequency in nature. In that case, we are having an inbuilt transformer inside the nacelle of the wind turbine, and we are having a grid connection at that point. One more option at this voltage is usually it is, as it has been mentioned over here, greater than 1000 kV, we are having a HVDC connection that is to be run from the seabed to the shore bed. The reason is very simple. We can carry only two conductors from the seabed to the shore. So first we will start converting this AC to DC conversion. It is there inside the nacelle of the turbine. Then the two DC cable with plus and minus polarity, it will come out, and we can run these high voltage DC connections. And at the shore, we are having DC to AC converter, that is inverter. And ultimately the power has been supplied into the loads, into the conventional Indian grid or conventional country grid as a whole. So this is one of the giant wind turbines. It is first offshore wind turbines that has been installed. So this is called the technological revolution. Now, talking about the conventional comparative analysis, we are having the 4 type of system. The first system is type A system. In type A system, we are having the fixed speed wind turbine concept. In that case, we are using the induction generator or a squirrel cage induction generator, and the gearbox is required. Over here, the capability of the induction generator is to generate only active power. So we need to accommodate some capacitor banks to supply the reactive power. Otherwise, this induction generator will not feed electrical power into the grid, and the gearbox is of massive gear ratio because we need to turn our rotor at super synchronous speed. This could be achieved from both the way. If you can go with the wound rotor induction generator with having the slip rings over here, the soft starter is not required because the torque has been already controlled using this wound rotor or the rotor bias that is to be interfaced with the 3-phase resistance. The third aspect is known as the doubly fed induction generator. So the power has been fed from both the direction. This technology is again renowned for the wind energy application. The first is the DFIG, means first part is it could be covered by DFIG by stator and rotor itself, because this wind turbine through gearbox, it is connected with the rotor and the power is generated through the stator, and this rotor and stator both are connected with the transformer and the grid. We are having the controlled rectifier and the controlled inverter, so we can manage the power from both the sides. Usually the power has been shared by 70% from the stator side and 30% from the rotor side. Over here, some grid operator might be observed by connection and disconnection of the machine. These are things that could be discussed in this session at a glance only. You will find detailed chapters in theoretical books, how you can change this operation of DFIG and other generators. And the last one is the type D system. In type D system, this gearbox has been obsolete. So it's a direct drive system. No need to go for this gearbox. If you need gearbox, then you need to reduce the pole of the permanent magnet synchronous generator. Then it is connected with the controlled rectifier, then controlled inverter, and then the transformer, which is connected with the grid. So these are the 4 types of system that could be observed in the case of the wind energy conversion system connected with the grid. Now, these are the comparative analysis of the wind generators. With a lack of time, I am not going to consider each and every point, but I should focus on the certain disadvantages or the limitations of the squirrel cage induction generator. So its excitation makes it difficult to support the grid voltage. So we need to excite this machine to feed the reactive power by incorporation of the capacitor bank because it is not at all self-excited machine. Talking about the wound rotor synchronous generator, it requires a very large space to accommodation of the excitation winding and pole shoes. Obviously, if you can accommodate this pole shoe, the field losses are obviously more and it is invited. Talking about a variable speed double-fed induction machine. So we are having the slip ring that is required the rotor power by means of partial scale converters. That is what we call VSC, voltage source converter, which needs a regular maintenance and may cause some electrical machine failures. This DFIG was not LVRT capable. In few cases, still this system is there. Current DFIGs, they are LVRT capable, but it will encounter certain disadvantages. Talking about the main feature of permanent magnet synchronous machine direct drive system, as our rotor is of permanent magnet, which doesn't require any external excitation from the grid or from the other DC supply, which is not required. So in ultimate case, we are having the various aspects of diode bridge rectifier. It may be used as a generator terminals. Fewer rotating components are there. No gearbox, so the cost has been reduced. The amplitude and frequency of the supply voltage can be controlled. It creates the less noise and pollution. Talking about disadvantage is the cost and difficulty of the manufacturing. And if you can install this kind of PMSC concept at the large scale, it might be a problem of demagnetization of permanent magnet at high temperature that has been observed. So these are the terms related with the wind turbine. First is known as the cut-in speed, the speed at which the wind turbine starts to operate and it will start generating the electrical power. The second, which is not mentioned over here, is known as the startup speed. The startup speed of the machine is usually the turbine will start to rotate, but it will not generate a sufficient torque to develop the electrical power in positive side. Positive side means the generation of power. The second is the cutout speed. The cutout speed at the speed at which the speed of the wind turbine, it will stop the production and turns out to be the main wind direction. Now, there is a wind direction. Wind direction is changing continuously. So, our wind turbine must be oriented towards 90 degrees with respect to direction of the wind speed, and hence your turbine will rotate. The second is design wind speed, when wind speed will be at its maximum efficiency. Then rated wind speed, when the machine or a generator reaches its maximum power output. Then it's a tip speed ratio. It is the speed of the blade tip divided by the wind speed. For example, if the tip of the blade is traveling at 100 miles per hour and the wind speed is 20 miles per hour, the conversion of meter to second is already shown, then our tip speed ratio is simply 100 divided by 20. It is nothing but the 5. So the tip of the blade is traveling 5 times faster than the speed of the blade. And one of the most important factor is known as the power coefficient. So the power coefficient of wind energy converter is given by ratio of output power from the wind turbine divided by power content in the wind. So there are two basic type of wind turbine as a whole which is available. The first is the horizontal axis wind turbine and the second is the vertical axis wind turbine. In case of horizontal axis wind turbine, the axis of rotation is the perpendicular to the ground. In the case of vertical axis wind turbine, the axis of the rotation is parallel to the ground. However, there are some special machines known as vertical axis wind turbine. This is the concept of Darius rotor. If you can take this shape of the Darius rotor, it is nothing but the egg beater type. If you can hold the conductor likewise in your two hands, and if you rotate the conductor, it will become the egg beater type. It is also known as a particular profile named as Troposkian profile. And why it is special wind turbine? Because it works on the principle, on the same principle on which horizontal axis wind turbine will work. But these are the induction generator based wind turbine, and due to the first loop of the vertical axis wind turbine, we are having the same thing over here, but it rotates with the principle of vertical axis wind turbine, but it will generate the forces in context with the vertical axis wind turbine, though they are generating the power with the principle of horizontal axis wind turbine. So now we will start generating how much maximum power that we can extract from this. So if we are having the 90-degree wind is coming and it has been hit to the turbine and it will be passed away. So we are applying the concept of the simple Bernoulli principle. That is, pressure difference creates the velocity. As the pressure difference creates the velocity, in this case, we are having the generation of the wind. As it is generation of the wind, and the pressure difference will create the velocity, in ultimate case, your power output might be changed. And as your power output might be changed, at that time, we are having the various aspects of electrical power that is to be discussed. So now, suppose the wind is coming from the infinite side and it is heated by the rotor. At that time, we are having the pressure difference over here. So as per Bernoulli's principle, the pressure difference creates the velocity, and hence your turbine will rotate and the pressure will increase. Again, the pressure will go down. That will increase the velocity of the machine. So how we can derive the same? So if we can have the 3D dimension concept, we are having a disk over here. The wind is coming from the infinite direction. It will hit this disk. It will create the pressure difference. Whenever there is a pressure difference, it creates the velocity, small v. And this v infinite is the wind is coming from infinite speed or is from the infinite length. Then we are having the P infinite is a pressure over here. This is change in pressure. Then we are having the P infinite again. The pressure will be again the atmospheric pressure. But there is change in the wind velocity because this difference of this will be having the physical rotation of the wind turbine. So if you can apply this Bernoulli equation in the first section and second section, it is in the form of kinetic energy. Then it is half rho A V infinite plus P infinite equals to half rho this V cube plus P plus. Similarly, you can derive for the second portion. If you can subtract, this is P plus minus P minus. Hence, the pressure difference creates the velocity. That is half rho V infinite square minus V2 square, where V2 is this energy which is less than V infinite. So, initially, we are having one force known as the thrust force. So, this thrust force has been observed by the disk by having thrust is pressure difference time area. Thrust is also defined as change in momentum. So, if you can compare these two thrust forces, you will get one important conclusion that this small v is the average wind speed that is coming out from V infinite and that is coming out at the end of the generating a rotating frame of the wind turbine is V2. So now what is our main goal? Our main goal is to extract the maximum efficiency from the grid. So we need to categorize this entire scenario in these three cases. The first case is no wind, no power. Maximum wind, we are having the maximum power. Now in case 2, the V infinite is passing through without hindrance or a thrust. So ultimately, if there is no thrust, if I can say that, what is the wind speed in this room? It might be very less because I am encased in a room. So ultimately, all the four velocities are 0. Again, my power output is 0. Case 3, suppose a surface consists of very large power extraction medium like a valve. Again, our power is what? 0. So there is some logical interference factor known as axial interference factor. Later on, we can call it as a power coefficient or a CP. So logically, if you can develop A equals to 0, then no interference, wind will pass through the tunnel, and A equals to 1, that is nothing but the complete blockage. So in ultimate case, we need to find the value of A that can satisfy the equation optimally, that is A equals to 0 and A equals to 1. In between there is some value. So the wind can be easily travel from the windmill. So if you can define the optimal equation of wave, that is V equals to V infinite 1 minus A. If you put A equals to 0, V equals to V infinite is valid. If you put A equals to 1, V equals to 0, which is also valid. If you can put, suppose, any other equation, say for example 2 minus A, then 2 minus A is 1, V equals to V infinite, valid for a time. But if you can put V equals to 1 plus 1 over here, if you can put A equals to minus 1, then 2V infinite, how the incoming wind velocity is more than the outgoing velocity. So only one equation which is the best fitted for this value by defining A is V equals to V infinite into 1 minus A. And this could be compared with the value, that is what we have derived in this V. If you can compare this 2V, and mathematically you can incorporate this equation of V in the equation of power. This equation of power is half rho A V cube, where half is the constant, rho is the mass flow or a density, A is the swept area of the rotor, and V is the wind speed. Usually this equation has been derived in terms of half mv square, because wind is nothing but the kinetic energy and it is in particular density. So again it's a rho. So half rho A V cube, and instead of V, we are bifurcating this V into V square, and we are accommodating the value of V square in this equation, solving it, differentiating with respect to A, because the A is going to be changed continuously. We are having one ultimate solution of A equals to 1 and A equals to 1 by 3. A equals to 1 is not possible because it's a complete blockage. A equals to 1 by 3, if you can accommodate, you will get half rho A V cube into Cp. The Cp is 16 by 27, that is 0.59, is known as the Betz limit. This Betz limit is for horizontal axis wind turbine. So if you can use this turbine, which is horizontal axis, its power is half rho A V cube into Cp, where A is the swept area of the rotor, half is the constant, rho particularly constant, that is 1.225 kg per meter cube, and V is the wind speed. If you can detailedly model this equation for a particular wind speed, say for example, it is 10, then P equals to half rho A, which is constant, 10 cube. Now suppose your wind speed is 11. Obviously, according to change in wind speed, your Cp is going to be changed. But your power is proportional to V cube. It means that with very small change in the wind speed, there is huge impact in the power in case of the equation of the power. So this to be designed very perfectly. Without taking much time, I shall have a conclusion of this topic by having the another equation, that is 8 by 27. This is the power coefficient of vertical axis wind turbine. Hence, from this equation, I want to prove that the horizontal axis wind turbines are much more efficient compared to vertical axis wind turbine. Hence, what I observed in that two figures, I have intentionally keep horizontal axis wind turbine word over there, because that vertical axis wind turbine works on the basic principle of horizontal axis wind turbine. Now, this theorem is known as the Betz theorem, where from incoming wind power, 41% energy has been escaped with the Betz theory. So, remaining 59% theoretically, usually wind turbine observes the drag force. In drag force, 10% energy has been wasted. Rest of the 53%, that is 90% of 59%, will be still entering into the generator, because we need to found the energy chain. Then we are having the copper loss of the generator, and 20% heat has been already absorbed in terms of heat losses. So we are getting only 42% of the energy. But this 59% again is not achievable. We can have a 0.4 to 0.5 CP for large-scale grid-connected wind turbine. So this thing has been demonstrated using one design example. You may refer this link. You will get lots of other design data also. So we need to find the value. Obviously, it's not a theoretical class. It's a discussion only. But we need to find the power at different wind speed and the plotting the curve of the wind speed versus power and wind speed versus CP, considering rotor swept area of 2,198 meters square and the rho is 1.225. So this is what the characteristic of the wind turbine. What it tells that would be covered in this session after seeing this data sheet. Now in this case, we are having this wind speed over here. This arrow shows the cut-in speed. This arrow shows the rated speed. This arrow shows the cutout speed. Now, after having this power, we can implement this half rho A CPV cube. Half is again constant area, which is given over here, 2198 meters square. Rho is given, which is constant, and CP is also given. So if you can accommodate all the value, if you can calculate using either pen and paper or a MATLAB program or Excel sheet, you will roughly get these values of power. It is depending upon how much accurate you are. So what it has been done, the first region in this power curve is the cut-in speed. The second is the constant CP region. Over here, the CP is almost constant. In third case, it is the constant power output region. See, again, this is a constant power output region. And in the last case, it's a cutout region. So what these things are telling. So if we can working on the constant CP region, so slightly the CP could be vary. And when this generator is of 800 kilowatt power, plus or minus 10% is allowable range. So after 12 to 13 meter per second, the power is constant and the CP is going to down. So if we are not focusing on the CP, let it be up always, then also the power rating is higher, because as per the equation, it is half rho A CP V cube. And power is proportional to V cube, then your generator might be burn out because you are working above the capacity of the generator. So after this 12 meter per second of the rated wind speed, there is pitching of the turbine. Are you getting me? That is pitching of the wind turbine by sacrificing the value of the aerodynamic efficiency of CP or a power coefficient and maintaining electrical power output constant. Then again, if you will check this characteristic, we are having the cut-in speed, then we are having the constant CP region. Once our power is reached up to the 1 per unit, that is the rated capacity of the generator, that is constant power output region. Again, when you will reach at this point, our stalling, active and passive stalling is incorporated, and then the turbine will go into the cutout range where we are having the yawing mechanism. Yawing means if you are having that toy, that is what I initially tried to describe. If you will rotate in the particular direction among its own axis, at that time it will stop at the particular point. And hence, the 90-degree between wind speed and the wind turbine, it will be not there, and wind turbine has forcefully stopped. If you can take an example of the same aspect, it is nothing but the tornado at very high wind speed. In technical language, it is known as high wind gust. And this is what the outcome of the characteristic. The first curve is known as the wind speed versus power output. See, at 810, the power output is constant. So from at this point, our characteristic enters from constant CP region to constant power region. And this is the change in CP. This is the 10 megawatt wind turbine data. see the cutout speed up to 30 meters per second. This is the advancement in the curve. Then we are having the Heliad X 12 megawatt, world's largest offshore wind turbine. So let's have a video so you can have a height of it. Usually this height is known as the hub height. Hub height can be measured from the ground to the top part of the hub. And this is what the height of Heliad X. So again, this gigawatt capacity per wind turbine is going to be increased. Now, how this wind turbine works upon? So basically, there are two forces. The first is the lift force, and second is the drag force. If you can visualize these two forces, this is very easy to demonstrate using this small example. This is the drag force and this is the lift force. Now, if you can apply these two forces on the wind blade, then how it is supposed to observe. So this is the lift and drag force in the stationary foil. So over here, if two person can start running at the same point, this person takes less time to reach over here, this person takes more time. So over here, higher the air flow, lowering the pressure, and slower the airflow, higher the pressure. It means that the pressure difference will create the velocity. It will start rotating. If this blade is not connected with the hub, then it will move away. But as it is connected with the hub, it will start rotating in this direction as it is static in nature. In similar way, we are having the lift and drag force in translating airfoil. So in translating airfoil, our V in that figure, and in this case, the wind speed is also changing. Relative airfoil motion is also changing. So we can develop the concept of relative wind, and at the same direction of the relative wind, we are experiencing the drag force. With respect to drag force, 90 degree, the lift force will be there, and there would be change in the speed of the turbine with the change in wind speed. Otherwise, the windmill will rotate at the fixed speed because the wind speed is not changing. So if you need to experience the same thing, you can have your hand outside from the driving car, and if you start lifting it, you will find something panic in the arms. It is nothing but the lift force. The same principle could be offered in the case of the airplane. In airplane, the drag force has been minimized or nullified using jet engine. Now, in case of wind turbine geometry, I'll just focusing on it little. So we are having the chord line over here. This is the relative wind, and this is the angle of attack. So particularly in case of angle of attack, if you will higher angle of attack, your lift force is going to be reduced because it is turning out of the wind, and this is our resultant force. So how these forces are acting on it? So we are having the airfoil of this cross section. We are having the V is coming from this direction. V is the wind speed. So we can plot this V over here. U, that is the rotation of the wind. So U is towards hub, minus U is on opposite side. And if you can have a particular simplification of V and U using parallelogram, we'll get the W, that is relative wind speed. So at the direction of relative wind speed, we are having drag force. At 90 degree of drag, we are having lift force. Resultant of that is the net force at which it is having the rotation of the turbine blade. And this is what FM. FM is due to gravity, and this FM is known as M. M stands for moment producing force. Now, this discussion is at a glance. So how we can draw this diagram? So first we are having the V, then we can project it from the center of gravity of the blade. Then we are having minus U because U is in this direction. Then we are having its simplification using parallelogram. You will get W. In the direction of W, we are having the drag force. At 90 degree of drag force, we are having the lift force. We can have a parallelogram again. We'll get the net force. And this is our moment producing force. And this angle is known as the blade pitch angle, beta. There is always cheat sheet available over here to select the drag coefficient. So we are using either half streamlined body or streamlined body shaped airfoil to generate the power using wind turbine. These are the effect of angle of attack and blade forces. If my angle of attack alpha is 4, this is our lift force. If it is 12, still the lift force is rise. After our wind turbine is reached up to the stalling region or in cutout region, then your alpha is that much high, the wind turbine will not rotate. The lift and drag force are equal, or it might be drag force is little bit more without damaging the blade, because there is a tall structure. We cannot take it out from the turbine, but there is a possibility of this situation is very low, because in day-to-day life for 1 to 2 years, the people are constantly measuring the wind speed and they can plot the histogram as well. So from that, they will be able to conclude what is the rated wind speed at this site, and according to that, they will select what is the rating of the wind turbine and wind energy generating system. Now, I will start to demonstrate about grid integration of wind generator with its simulation analysis. This is, as I mentioned, it's a gearless system now. Previously, I have shown the gearbox, but it is optional. Then we are having the wind turbine control system. We are generating the reference voltage and reference current. This simulation has been demonstrated in the PCM simulation tool. We are having the wind turbine model. It is connected with the permanent magnet synchronous generator. Then we are generating the voltage and current. From the generator, which is ABC, it is fed to the 12 pulse converter, then the inverter. I'm thankful to one of the industry in Gandhinagar, MTech Electronics Limited. They have offered me a industrial platform to perform this task and some hardware test measurement. This inverter is connected with the grid via transformer. So this is our grid current. This is our grid power factor. As initially I mentioned that this grid power factor is usually nearly equals to 1 during healthy condition. This is tested for 12 meter per second. This is a generator voltage and generator current. It is enriched with some harmonics because over here, this 12 pulse converter is not in closed loop. This is inverter voltage, inverter current. This is DC link voltage and DC link current, which is around 680, because at 680 plus or minus 10% limit, this is the voltage of inverter window. This is the simulation of the same turbine I tried to explain of Enercon E53. This is the RPM and this is the speed of the machine. If you need to accommodate the gear, these are the hardware testing of an inverter at the industrial premises. We are getting the same results in the hardware also. Now, when there is a fault into the power system, at that time, there is a concept, as I have tried to explain in the earlier part in a very short manner, that is LVRT, that is low voltage ride through technology. So when there is a fault, the voltage will go down. See, this is line-to-line voltage. When there is a fault at this moment, it will go down. Now the power system senses that this is temporary fault. Then at the end of momentary fault, within 3000 milliseconds, the 80% voltage has been regained. This feature of the turbine generating system known as FRT or low voltage ride through LVRT. This is the common example of the comparison. Without LVRT option, it might be a trip, and with LVRT option, it might be a survive, and the power will recover quickly. With the incorporation of FACT devices, they will provide some power in this duration, so the wind turbine is tightly connected with the utility or a grid. So now in this case, if there is a double LG fault over here from the grid side, line to line fault and line to ground fault, then this is what the increment in the grid current, decrement in the power factor. This effect is known as FRT. However, the grid connection is tightly connected, so that there is no collapse in the current, there is a collapse in the voltage known as the FRT. Now, if you can zoom it, it is still less than the tripping time of the relay. So again, the relay will not trip over here. And this is the rise in DC link voltage during fault time. And these are the active and reactive power flows at the fault time and the VA capacity of the machine. Now, in case of triple LG fault, this is what the LVRT. This is the exact demonstration through simulations in the low voltage ride through. And this is the zoomed view of FRT. Apart from that, we are also having a model of standalone wind energy system. In case of standalone system, we are having the various aspect and simulation analysis of the standalone system. Usually at the rooftop, in case of India, we are not having much wind speed, but still we can harness a small wind turbine, which is of horizontal axis wind turbine. We can charge up or we can turn up small loads, and the vertical axis wind turbine for the battery charging applications. So this is the simulation analysis we performed. This is the direct time system. It is connected with the permanent magnet generator. We are having uncontrolled rectifier and the boost converter, which is fed to the DC load. And it is given this signal has been sensed, that is current sensor and the voltage sensor. We are sensing the input signals. We can generate either voltage reference or current reference depending upon the algorithm of MPPT. Then it is given to the PI or any other adaptive controller with the suitable switching frequency, we can generate the triangular waveform, and we can turn off these pulses. Then we also apply the case study with the sudden change in wind speed. That is, this is the change in wind speed. This is the change in wind speed. This is the change in voltage. This is the change in power. This is the system of 3 kilowatt. And this is the change in current. This is also studied for variable change in wind speed. So this is the variable change in wind speed for 50 seconds. This is what the wind speed pattern. This is what the change in voltage. This is what the change in power. And this is what the changing in current. In variable wind speed, we have doubled the effect of the generator, that is up to 6.5 kilowatt. This is the work proposed by our current PG student. In case of modification of simulation in the standalone system, hence this manuscript is under review. I cannot share the results of this task, so I just pasted the result table, what we are getting with the various permutations and combinations of 2 MPPT algorithm, because at the initial part we have discussed the tip speed ratio and the DC side control. So in both the cases, one can apply the MPPT algorithm. So if you can apply the MPPT algorithm with the variable current perturbation, it could be showing this result. And in second case, we are having this variable step P and O MPPT algorithm. We are achieving some different results. But though the MPPT effectiveness is at above 95 to 99%, it could be vary, because this system is also tested for various loading conditions also. So I am thankful to this student for having this achievable task and comparing this table. Now this is our last segment of the wind farm project timeline. So we are having a development stage. It took up to 10 years. Then we are having implementation stage. It took 1 to 2 years. Then operation, and then decommissioning, if you need to have a repower or remove that system. Now, if you can talk about the costing of wind energy conversion system. So we are having the economics of wind farm. So first we are having the development, site assessment, wind resources, permission if you need to take, legal contracts with other companies or other stakeholders. Then the second stage is the implementation. We need to identify the site, because nobody will acquire this big land. So we can contact nearby farms and the landholders. What we can do with them, we can sign the agreement, we can sign the MOU, or we can go with the right-of-way costing. Then cabling, and this entire windmills that I tried to demonstrate you with certain wind turbine rows. And that wind turbines are situated anywhere nearby the substation. So at that time, we need to go for cabling at point of coupling and grid integration or grid connection at the point of common coupling. Third is the operation, maintenance, or administration. And the fourth is the decommissioning. Now, talking about the costing of the same, this much cost is required. Almost 65 million euro is required for the development purpose. Almost for 2 megawatts, this was 40k euro required. I also transformed into the Indian National Rupee, so I will be able to know that. And similar cost is used for the decommissioning of the wind farm. However, the implementation cost comprising of various salaries of the employees, turbine foundations, etc., which is depending upon the person to person and company to company, this might be vary. Now, what is the concept of the hybrid system? For the standalone system, we are having a DC generator-based system or a AC-based generator wind system. It has been merged with the solar photovoltaic system. It can be also merged with the diesel generator, that is conventional plant. It can be also accommodated with the solar battery combination. It can be wind battery combination. Over here, the grid is not involved. So it is concept of standalone hybrid system. You may refer this link to know further about the challenges and issues of the complex hybrid system. These are various modes of hybrid system where we are having the wind, solar, diesel generator, AC load, DC load combined. Turbine, you can turn on, turn off, turbine controller. We can have a resource center. In form of GIF, I tried to explain this thing in the initial part of the session with some grid management techniques. So as far as concluding remarks are concerned, ultimately, the wind power is obviously superior as compared to all other power because of the generation from a unique point. If we are having the Heliadex offshore wind farm or offshore wind turbine, we are getting huge amount of 12 megawatt power, though it is at rated wind speed. But with the proper planning and the development, we can have a good efficiency and up to the rated capacity of the generator. Talking about the Gujarat, for wind power, we are having a tariff rate of 2.43 rupees per unit for grid touch system. And by 2022, particularly India is going for 35 gigawatt offshore wind project. And we are the state with the Tamil Nadu. Gujarat and Tamil Nadu are found as a hot spot for this offshore wind installations. Talking about the standalone purpose, we are having the more feasible solution where we can charge the battery, empowering our home, or we can accommodate the solar and we can harness the renewable power, or it can be also hybridized with the conventional grid. There is one laboratory known as NREL, that is National Renewable Energy Laboratory, situated in Denmark. You can just refer the website. You will get each and every detail of wind power improvements and what we are doing right now in this era. So again, the same thing, let's pray to God and Almighty that we all will be safe and will remain safe from this pandemic situation. And thank you. And I'm thankful to all the coordinators, all the volunteers, all the listeners of this session. Now I have not covered lots of things. What are the mechanical sides? I just want to share the same with one video so you will be able to cover the things easily. This is the frame size of the turbine. This is a shafting. This is interfacing. See how giant generator is. This is foundation. So thank you to all again. Thank you.
Thank you so much, sir. It was really an informative session on WES, Wind Energy Conversion System. And especially, I must say that the whole content that you have explained, it is in a very easy manner so everyone can understand. And we got a deep knowledge about the power generation through WES and wind energy system, the efficiency of the power generation through wind energy, the national wind energy mission, that the detail what you have shared, the different types of generator used in a different types of wind system, the efficiency of the wind turbine, as well as the costing of wind energy conversion system that we implement. uh, Really, sir, it was a very informative session for the student
Yes,
as
sir.
well as all the participant. And
Thank you.
I must say that this session will be useful for everyone to think in different perspective, as well as to cope up with the latest trend and technology which is running into the industries or in the market for generation of the electrical power through wind energy. Thank you so much, sir, for sharing such a precise knowledge as well as your experience with us. Sir, we have some question from the participant, and
Yes,
the
sir.
first question that was asked by Rahul, and that is on the screen, is asking
Yes,
about
sir.
that the fluctuation in voltage and grid frequencies are the major challenges in wind power generation. So, what are the solutions for that?
Uh, Actually, it requires a deep knowledge, but I will try to cover the same thing into 3 to 4 lines. First of all, there are two fluctuations. In case of voltage fluctuations, inverter will take care of that fluctuations. There is a window, like solar inverter, there is a big window available that is 10% of 680 volt in case of the system. I just discussed in that. That is 68 plus and 68 minus. That voltage is taken care by inverter assembly. In case of grid frequency disturbance, there is array connect disconnect. So that wind turbine is disconnected temporarily. It might be a change in frequency due to change in wind speed or other fault of the generator or converter assembly. And the second question is like disturbance. The solution is nothing but by that time we can go with any FACT devices. Ultimately, in India, we are having the FACTS controller, but still it is inside the laboratory. Or you can go with the LVRT capability machines. However, there are certain solutions and challenges of the convection power system. Likewise, thermal and hydropower plant is also implemented in grid-tied wind energy system for large scale, but still that result is not been achievable. So we are using the conventional technique, keep aside, and we are having the power electronic converter mechanism to address this kind of issues, particularly voltage and frequency.
Yes, sir. Sir, the Bhavya Pandya is asking that, sir, can you tell something about small scale wind energy conversion system for urban areas?
Yes, there are two aspects of small scale wind energy conversion system. The first aspect is the vertical axis wind turbine that is using for pouring the water from the ground. So we are having one option of 7 years rotor. So we can have a cylindrical component, we can cut it into two halves, then we can immerse one shaft and we can rotate that by pouring the water from the ground. For the urban area, if you need to go for a particular electricity generation, again, there are two aspects. The first aspect is horizontal axis wind turbine, but there are issues of bird heatings at that time. So people prefer vertical axis wind turbine. Again, there are two modes. In the first mode, through vertical axis wind turbine, because the generator is mounted on the ground, we can easily dismantle. We can charge the battery. Again, by implementing with the shaft, we can charge the battery and we can use our household devices with the charged battery. Or parallelly, we can charge the battery and we can use that electrical power.
Okay, thank you, sir. Sir, Dharmik Gohil is asking that how can we forecast wind energy, because
Okay.
it's stop just.
Okay. Actually, it requires 2 years to 5 years day-to-day measurement of every 15-minute data, incorporating that data with weather monitoring station, doing the averaging of speed, converting into monthly data, plotting the histogram, and you will able to know that at what particular wind will blow at this side, and from this we can able to judge what we can design the rated wind speed of the turbine, and from that rated wind speed of the turbine we will select the rating of the generator, because in that particular region this is the rated wind speed dedicatedly.
Yes, sir. Sir, we have covered almost all the questions from the participant, and all the participants are giving a feedback at here in the comment box that it was a really nice session and easily explained on such a useful topic, because many number of students in engineering are doing their project work in this area, like generation of the power through wind energy, generation of the power through solar, and for those all participants as well as students, this area will be very this session will be very useful, because they can easily understand what the knowledge you have shared. And sir, can you share your mail ID so
Yes,
the
sir.
participant can directly contact you through
Yes,
the
sir.
mail, or they can ask their query on that?
Yes, sir. It is there in my PPT. I'm going to share this PPT with you people. You may float it, or I
Okay,
can
sir.
type in this private chat window. You can just put it public if you want.
Uh,
Collecting Sachin a message કર્યો.
Uh, Chinmay sir is with us. Sir, you have shared your mail ID, and
Yes.
I am putting it into the comment box. So
Yes.
please, I request to the participant to please note it down this mail ID, so you can directly contact to the expert, and you can also ask your query if you have. Thank you, sir, for sharing your mail ID, and I would like to request Ravindra sir to please give a vote of thanks. Over to Ravindra sir.
Thank you, Siddharth sir, for sharing your valuable time with us, as well as your deep knowledge regarding about the renewable energy, and as well as this renewable energy, especially wind as well as the
જેને
solar.
મેસેજ એ કર્યું
We
છે
are
લગ્ન
totally
જવા
focused on this one, and in
હિન્દી પેલા કે
we covering all these things from the basic to the real-time parameter, all the analysis, as well as the installations and foundations of the wind power plant. So this webinar will be helpful for all the participants as well as all the students. So once again, from the RNGPIT college, I heartily thankful for you. Thank you for that.
Thank you all. Thank you, sir.
This is for all the participants that I have shared the link for us feedback and quiz in the comment box. You can give your feedback about this session by filling up the Google form, and your feedback is really valuable for us. Thank you for all the participants to being here, to being connected with us, to give your positive response. Thank you so much again to all the participants. Chinmay sir, I would like to request Chinmay sir to please say a few words about this session, the importance of this session for the student.
હેલો હેલો
Yes, sir. Yes, sir. We can hear you.
ગુડ આફ્ટરનૂન સર.
Good afternoon.
હા 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 રિન્યુએબલ એનર્જી સોલર વિન્ડ એ બાબતે આપણે સરનો એક્સપિરિયન્સનો લાભ લીધો, નોલેજનો લાભ લીધો, અને એ ફિલ્ડની અંદર આપણે કેટલું કરી શકીએ, જાણી શકીએ, એ પાછું સર પાસેથી જાણવા મળ્યું. થેન્ક યુ વેરી મચ સર.
Thank you.
For sharing your knowledge, and thanks for રવિન્દ્ર કે એમને ઇન્વાઇટ કરી અને સેશન ગોઠવ્યું.
Yes, sir.
Thank you sir.
Once again, thank you to Siddharth sir, thank you to all the panel members, thank you to Chinmay sir, thank you to Ravindra sir, and finally I want to thank all dear participants for your response. Thank you so much. Have a nice day.
Thank you.